everybody, today we're going to be talking about topic 1.2, net force. So let's get started. Things in blue are things that you should be writing down. So the definition of net force is the sum of force vectors acting on an object. So net and sum both mean that we're adding things together. You'll see this written algebraically with the symbol sigma. So a capital sigma, that means sum of, and then a capital F for forces means sum of forces. So we're going to be looking at the sum of forces in the x and y directions separately. So we'll see a lot of sum of forces in the x and sum of forces in the y direction. And if we add up those forces and in the x direction and in the y direction, things balance out, or the sum of forces is zero, we call that static equilibrium. And this could mean that the object is stationary, so it's not moving at all. So probably whatever you're watching this on right now is in static equilibrium, or it could be something moving at a constant speed. So something that's not speeding up or slowing down, that can also be in static equilibrium. So we're going to start writing some force equations in the x and y direction for the following examples. So here I have a sign hanging from one cable. Okay, so let's say it's attached to something. So we're going to look at what forces are acting on the object and then write algebraically the sum of forces. So this object here is hanging. So anything that's near or on a planet needs to have a weight vector. So we've got the weight, force of gravity pulling down. And the reason it's not falling towards the earth is because it's being pulled up by this cable. I'm going to label that T for tension. So if you have a cable or a rope or a string, you can label it T for tension. And there's nothing happening in the x direction. So for this problem, let's just look at the sum of forces in the y direction. I know that it's going to equal 0 because this is stationary. So what we're going to do is we're going to look at what we have in our situation, and we're going to replace the sum of forces with the variables that we have in our free body diagram. So with my typical system, I'm going to have positive y as up, negative y is down, positive x is right, and negative x to the left. So upward, I've got tension pulling upward, minus pulling down, we have gravity, or the weight, and then that still equals 0. So I can write it like that, or you can say that my upward forces are balancing out with my downward forces, so my tension and my weight have to be equal. All right, now let's look at a box being pulled across a rough floor. So here we have a rough floor and we have a box. And let's say that we're moving at a constant speed for this. Let's say I'm pulling this with a string. I'm going to pull to the right with some amount of tension. Rough floor indicates that there is some friction pulling to the left. This box definitely weighs something. And we're on a surface, so we have to have a normal force pushing us back up so we're not falling through the floor. We're going to look at the sum of forces in the x and y direction separately. So in the x direction, I have tension pulling to the right, so that'll be my positive force, minus friction pulling to the left. Those together equal 0, or my tension and my frictional force are equivalent. Same thing in the y direction. I'm at equilibrium, so my normal force minus the weight equals 0, or my normal force equals the weight. All right, so if we have to do this with angled forces, so let's say we have a box being pulled across a rough surface at an angle. So same picture as before, but let's just angle that tension force at some angle theta. Everything else looks like it stays the same though. I've got my normal force, my weight, and my friction. What we're going to need to do is focus on this angled force here, so my tension. And we're going to need to break that down into x and y components and then look at the sum of forces. So this tension force right here is pulling to the right and up, so it's got an x component and a y component. So I've got some x component pulling to the right, and my shortcut is to take that hypotenuse, which is just t, multiply it by the cosine of theta. Then I've got some y component pointed up. That's my t sine theta component. I could redraw this box here with just x and y forces. So force of friction to the right, t cosine theta to the right, or friction to the left. I've got my normal force up. I've also got t sine theta up. And then I've got my weight pointed down. So now when I look at my sum of forces in each direction, so I've got t cosine theta pulling to the right minus the force of friction. So that's my sum of forces in the x direction. In the y direction, you've got the normal force plus t sine theta minus the weight. And that equals 0 still. So depending on what you need to solve for, you can rearrange these equations and solve for what you need. But just remember to break that angled force into components. So let's do an example. What's the tension in each cable if 100 Newton sine is hung as shown below? So these two angles are the same, so I can assume that both of these tensions are the same. So I'm just going to label them both T. And I'm given the weight is 100 newtons. Cool. So I know that things are going to balance out in all directions. The x direction is not going to be super helpful to me because I've got something pointed to the right and left. They're both t cosine theta, and it's not going to give me any numerical answers. So let's look at the y direction. Each of these has a t sine 45. So to look at this, I'm going to look at sum of forces in the y direction. I know it's going to equal 0 because we're at equilibrium. I've got t sine 45 plus another t sine 45, or I've got two of them, we can combine them in a second, minus 100 equals 0. So I've got two t sine 45s. Let's add the 100 to the other side. Now we can divide both sides by 2 sine 45. And we should get t equals a number. It's 70.7. All right, here now we've got a few definitions and a few new equations. So the first thing we're going to define is gravitational field strength. So gravitational field strength has the lowercase letter g, and it has a little vector symbol above it because it is a vector quantity. This depends on the planet. We'll get more into this in Unit 3, but here on Earth, the gravitational field strength on the surface is 9.8 newtons per kilogram. So the Earth at the surface pulls with 9.8 newtons for every kilogram of mass. And it's going to be the same all around the planet, and it points towards the center of the Earth. So at the surface, all these arrows could represent 9.8 newtons per kilogram. If you're way out here in space, you're going to feel less of a pull. So you could draw maybe a few small arrows out here. And once we get to Unit 3, we'll have an equation to say if you're, 400 kilometers above Earth, what would G be? So look forward to that. Next definition is weight. Okay, so remember, weight is a force. It's how much is the Earth pulling on you. And our equation for F of G is going to be your mass in kilograms times G. Okay. So mass is in kilograms. G is in newtons per kilogram. So when you multiply those two, you're just left with newtons. So weight is different than mass. Okay, remember, mass is a measure of how much stuff you have. It doesn't matter where you are in the universe. You will have the same mass, but G is different. So you will weigh more if you were standing on the surface of the sun, if you could do that, versus on the moon. Okay. And that's because G is different. Oops, sorry. Last one on this page, Hooke's law. So Hooke's law is to calculate spring force. So spring force is equal to negative kx. That's a lowercase k if you can't read that. So K is the spring constant. It's measured in newtons per meter. And this is the stiffness of the spring. So if you imagine like a little spring inside of a pen compared to the spring in the suspension of your car, those are very different. And that could be measured with the spring constant K. And X is measuring the displacement of the spring. So how much is the spring stretched or compressed from its natural state? So the reason for the negative here, so let's say I have a spring that's attached to a wall here. Okay. Let's say it starts right here, but then I stretch it out to here. Okay. If I'm stretching it in this direction, so this is essentially my X pole. This is the applied force to the right. The spring force is going to be in the opposite direction, which is what the negative means. It just means opposite. So if you pull to the right, spring force is going to pull to the left. If you push to the left, the spring force is going to push to the right. So that just means opposite. And this graph here on the x-axis is how much did we stretch the spring, and then the applied force is on the y-axis. It makes a nice linear graph. And the slope of this graph will be the spring constant. So this is essentially F equals kx. So my y variable, my slope, and my x variable. All right, last bit is about friction. So our equation for the force of friction equals the Greek letter mu. So this is Greek letter mu. It's the coefficient of friction times the normal force. Coefficient of friction depends on the surface. So is the surface made of ice or is it made of rubber? That'll give you a different value. Think about it as how grippy something is. And for the most part, mu is between 0 and 1. Something really, really grippy might be more than 1, but it's not usual. We have two different types of coefficients of friction. We have a static, which means we are stationary, or kinetic, which means we are sliding. What happens is if you push something, it's kind of hard to get something to start sliding, but once you start it sliding, it gets a little bit easier to move. And that's because if you have two objects resting on each other, there's interactions at the atomic level that you have to break if you're pushing on something so that it starts sliding. What that looks like in the form of a graph. So if I'm pushing on something with an applied force and I'm measuring the force of friction, so I push on something, let's say I'm pushing on a refrigerator, and the force of friction keeps increasing, increasing, increasing until it gets to some maximum, and then it levels out. So this is the range where we're not moving. This is static, and this is kinetic over here on the right. We have some maximum force of friction here, and this is our maximum static force of friction. Okay, once you break those bonds, you end up with a smaller kinetic force of friction. And that's because, for the most part, the static coefficient is going to be greater than the kinetic coefficient. All right, last example. What is the maximum force you can push a 100 kilogram box on a rough surface before it begins to slide? So we're trying to find this maximum peak here. Rough surface. Let's draw our free body diagram. We're pushing, let's call that FP for F push. Force of friction to the left. We have a normal force and the weight. We know that the mass is 100 kilograms, and we know the static coefficient. So let's start with our sum of forces. Everything is going to equal 0. So sum of forces, let's start in the y direction. That's going to make our life easier. So I know that my y forces are balanced. So I'm going to go ahead and jump to say that my normal force pointed up has to equal the weight. And from just a little bit ago, we know that weight is equal to mg. So let's go ahead and replace that, substitute in. So the normal force is equal to mg. That's useful because I have both of those things. So this is 100 times 9.8. So my normal force is 980 newtons. That will be useful here in a second, but it's not what we're looking for right now. We're trying to figure out the maximum force I can push with. So if I look in the x direction, my push to the right has to balance out with my force of friction to the left. So push force equals the force of friction. I'm going to do another substitution here. Force of friction equals mu times the normal force. So let's substitute that in. I already solved for the normal force, so I can substitute that back into for this number, and I'm given mu. So FP equals 0.8 times 980, which is a number that I have written down somewhere, 784 newtons. All right.